Awesome. All yours.
Okay, cool. Yeah. Yeah, thanks for the invitation. So yeah, right now I think we can start. And yeah, hello everyone. My name is Zuohui, and I got my PhD in Rutgers University, and currently I'm a research scientist at Meta. And today I'm going to talk about what I delivered in my PhD studies. And the short like title is like towards the human-centered recommender systems with knowledge graph assistance. Yeah, my PhD focused on information retrieval, natural language processing, and the recommender system, especially focusing on the trustworthy research over the recommender system with explainable, fair, and and also the faithfulness. And currently, I'm a research scientist at Meta, working as core ML. Yeah, that's a short bio, and you can feel free to read my publications through my website. Yeah. So yeah, that's. So this is a kind of joint work that collaborated with Dr. Yi Kunxian and my two advisors, Gerard DeMello and Professor Yufeng Zhang. So yeah, this is the outline, and as we know, recently there has been extensive research in developing intelligent human-centered AI systems, which can support human participation. And also we believe it will facilitate all the cooperation between the humans and the machines. But most of our current AI system will focus more on the model design, but less on the human participation as part of the pipeline. So as one of the typical decisions making paradigm AI recommender system have become a very important part in our daily lives, right? So in this talk, we can discuss several aspects of human-centered recommender systems with knowledge graph assisted. And this is the outline first. So I will introduce the backgrounds and the research challenges of the human-centered recommender system. Then I will discuss the explainable and fair recommendations, and also the human-in-the-loop paradigm. And two of the selected publications address the different aspects of the challenges, and I will go over them with some details, and also including the problem formulation, the AI model design, and also the experimental analysis. So yeah, nowadays we have like a kind of witness, emerging a lot of human-centered AI systems. For example, the many technologies that compose the intelligent web, user interaction systems such as like Apple Siri, the Amazon Alexa, and several other e-commercial conversational recommender platform, and also all of them serve as a direct interactive portal between the users and machines. It is expected to revolutionize our human-computer interaction. And for the intelligent agent in the human-centered recommender system, we hope it is able to like elicit user preference and also keep interactions with the users intelligently. And at the same time, it could be offer like explanations with certain suggestions. So, but on the other hand, the modern the current modern the human-centered recommender system should provide explanations to help users to better understand why such recommender decisions are made to the users. And besides that, the fairness issue also like arise because there could be a group of disadvantaged users may show like lower degree of activity on a recommender platform. I believe it will cause them to be less visible to the existing learning algorithm and be easily biased. So it may also lead to hurting the user trust towards the recommender systems. And as part of very important aspects, the human in the loop is kind of a branch of practical AI systems. It leverages both human participation and machine intelligence to establish the applied AI frameworks. And as we know, the human-in-the-loop learning, it has also emerged as essential tasks, which leverage the power of the machine and also power of machine intelligence and also the human intelligence to enable the collaborative human machine decision making. And in this way, we develop a human-in-the-loop learning paradigm for the conversational recommender systems. It is interactive systems which capable of eliciting users' preference and also utilize the user feedback to improve the overall performance. So yeah, we can focus on solving the fairness problem with knowledge-enhanced recommender systems. Since, as we know, knowledge graph has preserved a structure and also relational knowledge where that they can provide the item recommendations with explanations with the knowledge graph reasoning path. And before we dive into the detail, the traditional collaborative filtering framework, the recommendation could be just leveraged as a kind of a biparticle graph in prediction missing links. For example, whether the user A may prefer the item A or item B or etc. There's a kind of candidates, but there are some limitations. So it failed to provide explanations, and also it cannot to incorporate inactive users, because the inactive users may be more likely to receiving some unsatisfactory recommendations because they are also known as some cold start problems. And here we can start from before we dive into the fairness problem, we can discuss about the explainable recommendation over the knowledge graph reasoning. So this is kind of like a fundamental works, and which we have published in 2019 in SIGA. And as we know, knowledge graph is kind of widely used in a lot of IR tasks, including the recommendation and the design search engines. And in the knowledge graph, the final decision is to make a recommendation for the user. So in the knowledge graph reasoning, the reasoning path, for example, from the user A towards feature A until the item A, it can naturally serve as an explanation of such decision. So we start from the user A and recommend and also the intelligent system recommend the item A. And in terms of this, there are several paths from knowledge graph path from A to the item, could be this way or either that way. And both of them can serve explanations. For example, why we recommend the item A to the user A is because we maybe have purchased the item B before, and another user B who also purchased the item B like a person by item A. And that's why we recommend this product to the user A, because this formulates a knowledge graph reasoning, the path reasoning, if you don't consider about the direction. So it will help to use to provide intuitive explanation to users from the knowledge graph path reasoning. So then here, just the problem formulation of what I just talked about. So knowledge graphs preserve the structured and relational knowledge and make it easy to trace the reason for the specific recommendations. And here we have the user entity U and also the item entity I, V, and also the other entities, which such as the keywords from the user comments, the brand, the category, and also any maybe meta information that are related to the users and also the items, and also maybe some item descriptions. And also there's a relation purchase. So the task becomes very intuitive. So given a knowledge graph, how to predict the missing purchase link between the user and item. So there are two representative existing work where they are knowledge graph based explainable recommender systems that utilize the entities and the relations within the knowledge graph to augment the user item interactions. The left is the KG80, and also the right is our previous work. Both of them could be regarded, well, by that time as state-of-art explainable recommendations in knowledge graph. So it could be like better understand that user preference to the user preferences is very important to make the satisfactory recommendation decisions by like generating the explainable path within the knowledge graph from the user to item. And the extension of our today's topic is the fairness of such explanations, because in general, as we know, the active users like tend to purchase more products than the inactive users. And it's very intuitively that there could be exists more explainable path for the active users towards some like target candidates. Well, on the contrary, the less active users, and they have like a less purchase-based path. So their product activity is easily overshadowed by the active users. So in this way, we like demonstrate our promise, the promise, our proposed fairness-aware recommender algorithm, so as to provide fair explainable diversities, which can be like leading to the potential products of interest, especially for the inactive users. Yeah. So, however, yeah, current knowledge graph-based explainable recommendation methods that heavily relies on the historical data, right? So the recommendations and the explanations, they tend to be more consistent with the dominating active user interactions. The worst case is that if the model discriminates unfairly among the users, like in terms of the recommendations. And the second, the model may further discriminate between the users in terms of the explanation diversity. So under such conditions, if you think like when you're making the recommendation decisions, the explainable models will be subject to some like algorithm bias. Then the lack of the user item interactions will imply that the inactive user preference like are barely captured. It will cause the weak visibility of such users to the recommender system. So the issues become that such users will be treated unfairly in terms of both recommendation and also the explanation diversity. So our goal is to elevate such algorithm bias and improve the fairness of the recommendation decisions. And also there are some related works to algorithm fairness, group fairness, and also the individual fairness, where the group fairness we are now as talked about at the demographic parity. It requires that protected group could be treated equally, and also the individual fairness, which means the similar individuals should be treated similarly. So for each like specific domain, there is a need to design a suitable metrics to quantify the fairness and develop a new debiasing method, so that it could be mitigate such unfairness for the both group fairness and also the individual fairness. And yeah, I will also introduce our metric definitions later. So overall, after such like a long description, we can particularly seek to answer the following questions. The first is that how to verify our concerns about unfairness problem in explainable recommendations with such unfairness, and how to like elevate such potential algorithm bias, like to improve the recommendation quality while providing the diverse explanations. And whether our algorithm is able to consider both group level fairness and also individual level fairness, and whether our methods can process generalization ability to existing explainable recommender system method. So before we dive into the method part, we can go over with some preliminaries. And here the pi, which in knowledge graph, like big G is defined as a sequential composition of relations, just like maybe the user, for example, the user purchase item and the item's description is like is very cheap, so it's kind of just a composition of the operator on relations. So this dot denotes the composition, and here are the relations they are. And we specifically consider the user item path pi, where it's denoted by the L pi UV. The U is user, V is the item, which means given a kind of a user item path, there's like a path L. And such, we have also defined the user item path distribution, which means occurrence frequency is supposed to be the number of the paths with the path pattern like pi. And such distribution is this like function, and where the n pi is like denotes occurrence frequency of the user item path with respect to the pattern pi, and also the denominator is the total number of the paths. So because in that way, we can define the path distribution, which related to the explanation diversity. And in order to assess the like a difference in the path distribution between the two groups, we introduce like a symptom index of diversity. It is a very popular measurement in ecological science, and it measures the probability that two maybe randomly selected individual user item paths belong to the same user item path pattern. So the left figure, it plots the path distribution over the top 15, the most frequent path patterns. And we can consider the top 5% users as the active group, and the other 90% group are the inactive group. And we can observe the divergent distribution between the active and inactive users according to the group definition. And the right figure shows that the inactive group of users have less diversity in their path patterns compared to the active users. So in our settings, we consider a group of active user like G1 and also inactive user G2, defined according to the number of purchased item based on their historical records. And also in the following part, in this chapter, I may use like a capital I and J to index the like users and items like correspondingly. And the capital QIJ, which means it denotes whether the item J is purchased is select for top K recommendations to the user I. And our goal is to like pick up and re-rank the top K items from the existing top N results. And we use a scoring function F, which refer to some like a recommendation metric, such as NDCG or the F1 score. So as we have discussed in the like previous slides, right, the diversity of the path distribution, it leads to the performance disparity. And therefore we define the absolute difference of the recommendation performance diversity gap into two groups, like group levels recommendation unfairness and also the group level explanation diversity unfairness. The smaller FQ reflects the like explanation fairness score in terms of the diversity of interactions of the user. And the G1 and G2 are two groups of users, whatever the metrics that in like small FQ for the group 1 and group 2. So we use kind of like a averaging strategy to represent the user item explanation diversity of the two groups. So regarding to the individuals, that could be the similar story. And we using the Gini coefficient. It is commonly used in the sociology because it ranges from the 0 to 1, where 1 represents the maximal inequity, right? In the sense that one single person has all the income, and the other have the none. Well, the 0 means the perfect equity, where everyone has the same income value. And in our settings, the Gini coefficient is like adopted to quantify the individual recommendation on fairness, the individual level recommendation on fairness, and also individual level explanation diversity on fairness. So we can jump to the optimization algorithm in detail. So the explainable paths which provided by the original algorithm shows why the given item is recommended based on the historical user interactions. And it would not make sense to completely ignore every historical part of them. At the same time, we should also put the fairness constraints because it will raise path diversity as an additional concern. So based on this, our fairness aware optimization algorithm should consider the both historical records and also user interactions and the diversity of the generated explainable path between the user and item. So the path score, we weight the quality of the path, and we wish to consider the more varied set of the paths rather than just maybe kinds of the dominant historical user interaction data. So in this way, our path score will incorporate an explicit debiasing weight to adjust the bias of the user item path patterns in historical records. So for the path pattern pi and the user u, so this grade S score as a coefficient, it expresses the preference adjustment for the user. And here the L path is a scoring function where could be computed using the baseline methods. And here, also the omega pi, it represents the weight of the path pattern pi in generated user item path in knowledge graph. So we consider the fairness with regarding to the explainable path diversity. So let's say the big pi could be the number of the valid, the big pi, the number of the valid user item paths in the knowledge graph. And here the n represents the user of the path that appeared in the path finding procedure. And we can calculate the Simpson index diversity of such UV pairs, right? Such as like using these formulations. Then by aggregating such path score and the diversity scores, you can calculate the fairness score for the user UI that defined as f smaller FIQ. It could be used to calculate the group level explanation on fairness, and also the individual explanation on fairness level. So but we still need to rank the top K items to determine which order that they are present, which means we create a top K recommendation list with item ranked in descending order by the optimized recommendation score and the fairness score. So which means they have the original recommendation score. Here is a fairness score. It's kind of like a weighted sum. So right here in the alpha and beta, it's just acting like scaling effects. So therefore, we can formulate our optimizations as follows. Here, epsilon1 and epsilon2, they are representing some recommendation performance and also the fairness disparity of baselines. And moreover, the optimization, this could just be extended to individual fairness constraints. In this way, the core idea behind, we hope, is not too complex, because it just could be cast as 0-1 integer programming optimization problem. So here are the results. And first, we can show the both recommendation improvements and also the fairness improvements if you compare the original like knowledge graph-based explainable recommendations and fairness constraints method. So we can see the recommendation performance of the active users is much better than the inactive users, right? I mean, originally. It means that the active users are expecting more better recommendation experience. Maybe like they are economically more advantaged, and so that they can purchase more products in the system, and they can like insert more training data into the recommendation system model. So because of this, the inactive users, they will be like dominated by the ML machine learning algorithm, and the model will be biased. So sometimes you can see after our constraint, our fairness aware constraints adopted, you can see some improve the recommendation experience for both active users and also inactive users. And also, but sometimes you can see that the like inactive users here like got boosted a lot, but the active users will got some sacrifice. But no matter which case, the overall performance they got improved, because I think there will be more users, more inactive users, because we quantify the 90% like percentage on inactive users because they occupy kind of like a majority of the systems. So here are the case study where it reflects the fairness, our fairness aware algorithm in terms of path diversity and the accuracy of the prediction items. So the upper part is a vanilla like knowledge graph based recommender system, and it outputs the original like a path, which it doesn't consider about the path diversity, right? And also the explainable path connect to like 4 candidates. But for the same user, because after adding our fairness aware algorithm, the model is able to predict 6 correct items, and the user, and also it's reasoning why the user may will to purchase such items, and associate with more diverse like knowledge graph explanations. Yeah, so they are from the same users, but at our like improved fairness aware algorithm, we can make the 6 correct predictions in top 10, or the original are only 4. So a short conclusion in this work, we studied the problem of fairness in the context of the explainable recommendation over knowledge graph reasoning. And we first quantify such unfairness at the individual level and group level. And based on this, we propose the fairness metrics in terms of the like path diversity as well as the recommendation performance disparity. And we then present a generalized fairness algorithm that is able like not only reduce the unfairness, but also improve the recommendation performance. So next, we develop a human-centered loop learning paradigm, especially for the conversational recommender system, where such interactive system is able to eliciting the user preference and utilizing the user feedbacks to improve the overall performance. And specifically, we designed and built and evaluate 2 systems based on the open public dataset to the community. So this is the human in the loop learning. So it has emerged as a kind of essential way to utilize both power of machine and the human intelligence. In this, so that we can hope to enable such collaborative between the human and the machine. And very intuitive example is like guessing the number game, right? In this game, if a user has created a secret number in his or her mind, the system will interact with the user through conversations by asking quite a lot of questions. So that after multiple rounds to narrow down the range of the possible numbers until the correct answer is identified, but the user should like provide some correct feedbacks to the machines. For example, if your guess number is larger or smaller, it gradually will shrink until the final, the machine can guess the final numbers. Well, the user responds to the questions by telling the system right is whether too low, too high. In this process, the user will serve as a supervision to the system. The benefit of such human-involved feedback is that it will reduce the search space in guessing process and improve the efficiency of the algorithm. So there are some existing like practical related work which utilizing the user, the human in the loop paradigm. The first one, this one is to allow the humans to debug and improve the deep types classifiers by disabling the hidden features which are irrelevant to the classification tasks. And the second is the concept learning in computer vision. The proposed framework supports the human in the loop visual concept learning and uses the extracted visual concepts for the fine-grained model diagnostics and the comparisons. So this way, it integrates the human knowledge and feedback to train a concept extractor. Very little human labeling effort with very little human labeling effort. So in our real-world human-centered tasks, let's take a conversational recommender system as an example. So we use human in the loop as knowledge graph reasoning to develop the explainable recommender systems. So the key idea is to conduct the transparent dialogue state tracking over the knowledge graphs, as shown in this figure. So starting from a user node, right? And the system at various steps, it will needs to determine how to move to the promising neighboring node, and finally arrive at a potential item node or to that recommend to the user. So in this way, we can propose a human in the loop graph reasoning paradigm, where in this way the human is allowed to provide feedback to help the system to prune the irrelevant actions, and it can help to quickly locate the correct path towards the candidate node. So specifically, we design a unified knowledge graph G here as a set of triples with a start entity, relation, and as well as the end entity. The entity contains the source user node, the target item nodes, and also the descriptive nodes. The path L here over the graph is a sequence of entities and relations. And for the transitional graph reasoning tasks, given a source node U, the given a source node U, the goal is to find a multi-step path where the end node is regarded as a prediction. So in this way, to facilitate the human interaction in the graph reasoning, at each step, so the agent will generate a question Q, based on the traversed path before, and to ask the help from the user. Then the user will provide a response R. That may be a direct answer to the question, but it could be also consist of some ambiguous statements. For example, just maybe yes or no without informative feedbacks. So our task could be formulated as given a source node U and a non-target V. The workflow of the human in the loop graph reasoning is defined as follows. So at every step, T+1, given a traversed path LT, and the past all human machine interactions, the agent is designed to conduct 3 tasks. The first, it aims to find the top K path L T+1 to the descriptive node. And second, ask user a question Q+1 Q T+1 conditional on such LT+1 and receive a response R T+1. Third, it will also make a decision by predicting top K target nodes. So after we describe our tasks and we draw the data set based on the Amazon review dataset is a public one. It includes extensive user reviews and rich item information. So in order to enable the graph reasoning, we first construct the heterogeneous logic graph with rich metadata information of the user behavior and the item data. And we extract the keywords from the user reviews and identify the specific aspects of the items from the user historical records. And also it will provide multiple categories of user records, such as like purchase, comments, etc. And for the conversation generation, we just employ some like a template method formed by someone. So given a sequence of attribute entities, it will transform each attribute entities into a questions through language templates. Then we can randomly determine the user response to the question with the answer yes, no, or maybe unclear answer. Maybe, for example, I'm not sure, I don't know. And also with some predefined probabilities to mimic the real conversations. So in order to validate whether such constructed conversations follow the cost to find properties, we also conduct a human validation experiments. So the cost to find is kind of like maybe when I start interacting with machines if have no backgrounds, they may start to answer some course like questions, then gradually to reach out what may specifically target at. So that's a kind of like cost to find, like a paradigm. So here are our evaluations of human validations. It justifies our dataset constructions. We illustrate using the box plots with the degree of entities in cost to find manner. So as the dialogue turns increase, the degree of the entities with the turn decrease, because it is natural to start with a broader, more general questions, right? And as the conversational loops just process in a cost to find manner, the agent will gradually propose the fine-grained questions, some towards some specific characteristics, the specific colors, the flavors to the users. So in detail, we propose some benchmark method consisting of a set of encoders. So remember the three tasks we designed. Here, we also have three predictors for the different outputs as the low-dimensional vectors. And there are also three. Also, we consider the graph representations, dialog representations, as well as the embeddings as designed encoders. And the proposal task includes the next question prediction, which relies on the dialog history, and the next question prediction, which relies on the dialog history and the descriptive attributes to select the next questions. And also we draw on the dialog history and previous attributes to predict the next attribute entities. And also the recommendations predictions should be designed. So we also integrate three tasks with all the encoders into our end-to-end system. So here we can see the performance of our selected baselines and our benchmark methods on the some sub data sets. And the results indicate our approach obtains the best results compared to the prior baselines. And also we assume the users may occasionally they may struggle to provide useful information to the agent, right, to the machine, right, since they may initially may not be aware what their preference at first. And the agent should learn to ask right questions given the past conversation context. So our benchmark method not only takes advantage of the extracted entities within our graph, but also model the user feedback within the conversational turns. and it will enable. I think that's why it outperforms the other baselines, because with most of the evaluation results, and also we adopt like a standard evaluation recommendation performance, including this recall and MAP score. So in generally, it could be regarded on the surface, right? There's a dialogue. For example, when the user asks, "I would like a snack. Could you please give me one?" Right? The agent will interact with the user by asking several questions. So, for example, do you wish to try some dark chocolate? If the user say no, the agent would possibly ask another question: do you prefer the vanilla flavor? So during the conversation or as the conversational loops moving forward, the user may ask why these type of questions in the middle of conversation. But here I only give an example, maybe the statement. But the user may also ask why I would prefer the vanilla flavor, right? That's very possible. Then our agent should provide answers. So basically, if we can do human in the loop graph reasoning, the behind the system is that we can always track our dialogue state during the conversation, so that we can provide explanations. Then we believe it will make the agent more trustworthy towards the user, and the agent can justify such decisions without making arbitrary decisions. Every tracked the average answers that provided by the agents could be tracked over the knowledge graph. So yeah, that's the design of the human in loop graph reasoning. So in the broader sense, we view that this research has demonstrating the community how the human in loop paradigm can integrate. It can integrate like empiricism, like it kind of like machine learning, and also the relationism, the knowledge graph reasoning. This kind of the two major paradigms in AI research for the better performance and also the better explainability. Yeah, and here are my reference, and also you can feel free to read it through my Google Store or my webpage. Yeah, thanks for